Hello everyone. So today is the lecture 3 of Introduction to AI course. Today we will be discussing about evolution of AI, what is the perceptron theory, and what is the attention mechanism that is being popularly used in modern transformer libraries like ChatGPT and LLM models. So first, let us have a recap of what we discussed in the first and the second lecture. So in the first lecture, we discussed a lot of things. Firstly, we had an overview of AI. What is AI? What are its applications? What is human intelligence and what is artificial intelligence? What are their differences? What are their advantages? And similar things. We also looked into the similarities of artificial intelligence and human intelligence. Next, we also looked into types of AI. So there are mainly two types of AI. First is narrow AI, that is designed and trained for a specific task, such as image recognition or language translation. Second is general AI. So AI with human-like cognitive abilities, capable of understanding and performing any intellectual task, such as ChatGPT is an a general AI or an example of general AI. Next, we looked into some myths of AI. So, there are mainly five myths of AI that we discussed. First is AI will control the world. So, it is not the case, but AI will only assist humans in their day to day tasks. Next, we looked into AI systems. The second myth, that is AI systems are inherently unfair. So that is actually not the case. Any artificial intelligence depends heavily on the data that they have been trained on, and hence AI is not unbiased or unfair, but the input data is. If you are able to regularize or normalize the data that you are feeding in, AI will start acting unbiased. So this is the second myth that we have. Third is AI, machine learning, and deep learning are all the same thing. So which is not. We discussed all of these in detail. We'll be discussing a little more about them in today's lecture as well. So firstly, AI is a higher level branch. Then we have a lower level statistical branch of AI, which is called as machine learning. And thirdly, we have another even lower level of branch called as deep learning, which relies on perceptron theory as well as the neural network architecture. The fourth myth is about AI puts our data at risk, so which is actually not the case. AI is only able to understand numbers and is actually not putting any of your data at risk. It is only using your data to learn and not to harass or something like that. Next, we have all AI systems are black boxes. That is, we are not able to understand anything out of them. That is what they are learning, what are they understanding, what is the exact way that they are learning, etc. So, which is also again not the case. AI has far more readability in the recent times. There is a complete new research branch of AI called as explainable AI. So, explainable AI continuously talks about the features that the AI is learning on, and it talks about explaining how AI is understanding the world. So these are the top five myths that we discussed. There are many more. You can also discuss them with me whenever you find or trigger you are triggered by someone who talks a little about some mythical thoughts about AI. So, moving ahead, we also looked into the history of artificial intelligence. So, as we know, John McCarthy in the year 1955 coined the term artificial intelligence. Before that, there was a person who, Alan Turing, created a test called Turing test in 1950, which was able to understand how intelligent are machines becoming these days. So this is what the early stages of AIs were, and we can say that the birth of AI practically happened with the Turing test in 1950. Next, we had an AI winter where everything in AI, the investments were paused, and many companies didn't want to invest in AI. So, this phase of 1987 to 1993, we call it an AI winter. But in the late 1990s, many companies like IBM started to uh, put a lot of investments in AI related branches, and they indeed took the AI ahead. So this is what we call as AI winter. Next, we have AI agents. So we have multiple AI agents. We will discuss their types and the environment types. We already have like discussed their types and environment types in the lecture one, so you know that well. Next, we looked into some artificial general intelligence, which is transformer based architecture, etc. So these are artificial general intelligence models. You might have heard of ChatGPT, Gemini, Llama, etc. So these are some popular artificial general intelligence examples. Next, we looked into some AI applications. So we looked into AI applications in gaming, we looked in applications in healthcare, in business intelligence, in education, and we also looked into some popular algorithms that are AI based and are helping us in our day to day life. So, when you're typing a message on WhatsApp or any other platform, you are automatically suggested the next word. So, that is an excellent example of AI put in work. Second, you also have the autocorrect system in the same example. So autocorrect system is also nothing but AI which is correcting your spellings whenever you're mistyping them. Third, you also have recommender systems. Whenever you talk about something, let's say you talk about buying a guitar or buying something that commonly to your friend, your mobile or the AI that is sitting within your mobile is able to recognize those keywords, and the e-commerce platforms start recommending you those things only. So this is something is also we can call as an excellent example of AI that we have been experiencing in our life from a while. Next, we looked into how AI can help us in fraud prevention. That is, AI can help save, um, detect costly or fraudulent transactions and work on them or decline them on the moment, or at least confirm with the user that whether this transaction has been processed by you or something like that. Next, we also looked into intelligent agents and their types. So, what are AI agents and what are some types of AI agents that we have? So, first, let us talk about what are fundamentals of AI agents. So, we also looked into some fundamental of AI agents. So, an AI agent is an agent that is acting in a particular environment. So, the environment gives inputs to the agent with in the form of percepts which are received by the sensors of the AI, and these sensors based on the algorithm that is running within the AI decides which action to perform, and these actions are then performed with the help of actuators. So this is a very basic fundamental that we discussed in our first lecture of AI agents. So there are, let us now discuss some type of AI agents. So there are mainly five type of AI agents. First is model-based reflex agents. Second is learning agents. Third is utility-based agents. Fourth is simple reflex agents. And fifth is goal-based agents. We also looked into all of these agents one by one with their flow diagrams, how they work, what are their use cases, what are their flaws, advantages, etc. etc. We also looked into then we looked into some environments and their types. So there are many type of environments, and they always occur in opposite pair. So let us discuss this. We have single agent versus multi-agent AI. We have fully observable versus partially observable AI. We have static versus dynamic AI. We have complete versus incomplete AI environment. I'm sorry. We have competitive versus collaborative environment. We also have discrete versus continuous environment. We have deterministic versus stochastic environment. So, like we discussed a lot of, we also discussed examples of this. What do they actually mean, and everything in our previous first lecture. So I would want you guys to visit the previous lecture if you are not able to recall what it was. So this is all about what we discussed in the first lecture. Now we shall go through some content that we discussed related to the second lecture. All right. So the second lecture was about bridging AI history with current Gen AI. So we talked about how AI has been working on and how it has come to what it has been today. So first we looked into two basic particulars of AI. First is revisiting AI history and connecting it to today's Gen AI landscape, and also significant advancements from classical AI to generative models. So we looked into what was the AI history, some tracing its roots from classical approaches to the emergence of generative models. We will also discuss key milestones, influential figures, and the transformative impact of these technologies on various industries. We also looked into what is classical AI, that is the AI that has been working traditionally, the weak AI that we discussed in our first lecture. This is what we will be talking about. Then we talked about what is machine learning, what is the rise of machine learning. So machine learning, as you all might know, it is nothing but a statistical type of artificial intelligence which heavily works on statistical analysis to predict the future. We also looked into what is advent of deep learning. So the introduction of deep learning in the 2010s has revolutionized AI capabilities. Utilizing neural network systems became adept at tasks such as image recognition and speech processing, leading to breakthroughs that captured global attention and investment. Then we looked into what is generative AI or generative artificial intelligence. So, generative AI, as we discussed yesterday, is an excellent branch of AI that has been continuously working on not just predicting the future but also imagining new content. So, you can ask ChatGPT, which is a popular generative artificial intelligence model. You can ask it to write a story, write a poem, write a paragraph, or write an email, write a LinkedIn post, write an Instagram caption, or whatever you want. So, this is all an example of generative AI. So, we looked into some applications and history of generative AI. We looked into applications of generative AI in healthcare. We also saw that use case diagram where it was used for where Gen AI was used for healthcare, in drug discovery, in disease diagnosis, in personalized treatment plans, in research, in patient care, in medical chatbots, in predictive maintenance, in medical robots. Then we looked into some Gen AI in finance. So we have already discussed the fraud detection example in Gen AI in finance, but there are much more applications of generative AI in finance industry. We also looked into a similar diagram of generative AI. So there were some use cases like sentiment analysis, financial text generation, fraud detection and prevention, personalized customer experience, risk assessment and loan underwriting. We also looked into cybersecurity and risk management, compliance and regulatory reporting, trading and investment strategies, and chatbots and virtual assistants. So these are still some applications of generative AI in the industry of finance. Next, we also looked into generative AI in manufacturing or fabrication industry. So we also discussed some popular use cases of generative AI in the manufacturing industry. So they were like product design and development, supply chain management, customer service and support, production and inventory management, and predictive maintenance scheduling. So these are some top applications of uh, generative AI in the manufacturing industry. Then we looked into some applications of generative AI in education. So, generative AI or Gen AI is revolutionizing education by enabling personalized learning, automating content creation, and enhancing student engagement. It helps educators generate tailored materials such as interactive lessons and quizzes. So, we also looked into a similar diagram for AI in education. So AI in education is a broad category and it has a lot of applications. We discussed some of it yesterday in detail, and I'll just go through the headings that we have. So we have AI-based tutoring systems, we have personalized learning, we have translating languages, we have automation, we have grading and assessments analysis, we have voice assistants, we have real-time assessments, we also have personalized communication, we also have smart content development, and we also have collaborative learning through generative AI. So these are some applications of uh, generative AI in education industry. Then we looked into some advantages of generative AI, such as creative content generation, automated design, efficiency improvement, and predictive analytics. Then we looked into some disadvantages of generative AI, like bias and ethical concerns. We also looked into lack of control and resource intensive, since LLMs are very large. We discussed what is their configuration, whatever their RAM requirement is, etc. Then we also discussed about another disadvantage, that is misinformation and abuse that has been happening related to AI and especially in the generative AI industry. So we also looked into some ethical considerations. So as AI technology advances, ethical considerations become paramount. Issues such as biases, transparency, and the potential for misuse must be addressed to ensure that AI serves the greater good and enhances societal responsibility. So we also looked into some significant advancements from classical AI to generative AI models. We looked into some history of the development of generative AI models. We looked into what is the logic theorist. We looked into the first AI chatbot called Elisa, which was a rule-based system in 1966 that was developed. Next, we looked into the rise of machine learning and neural networks that has been happening from 1990s to mostly 2000s. And by the way, it is still going on, but currently the work is primarily going on in the generative AI industry. Then we looked into how the perceptron theory evolved in 1958. We also looked into support vector machines, which was developed in 1990s. Also, we looked into the deep learning revolution, which happened in around 2010, and then many convolutional neural networks and similar models were proposed by many MNCs in order to take the deep learning ahead. Finally, generative AI that has been here from a while has taken a boom since the development of an interactive chatbot called ChatGPT, which we'll be discussing in the further lectures, and we will be able to also work and prompt it. Then there have been a lot of mm, development in this Gen AI field. So we talked about the transformers model, uh, which is the heart of machine learning, or generative AI models. We also discussed about a very popular paper called Attention is All You Need. So this is a very deep paper. It has a lot of details that probably won't be would be a little difficult for you to understand at this stage of your course. But we will, in today's lecture, in the session number 3, we will go through some minute details of what is attention is all you need, what was proposed in the paper, etc., in a little bit of detail, and then we will move ahead in the same pattern. Then, in the key developments of generative AI, we discussed about transformers. We also discussed about DAL-E, which is a popular image generation model that has been offered from OpenAI itself. And finally, you had a homework kind of thing or an activity to do, which was timeline creation for AI evolution with current and future trends. So I hope you have completed it and sent it to me by now on my email ID. So yeah, that's it. What we discussed uh, in our previous lectures so far. Today we'll be discussing about the third session, that is AI evolution from perceptron theory to attention mechanism. So this is what we'll be discussing. Yeah. So let us start with the session number 3. Uh, First, let us discuss the particulars of session number 3 that we'll be discussing. So uh, we'll be talking about detailed exploration of early AI models like perceptron theory, the rise of deep learning, CNNs, RNNs, and the role of backpropagation. We will also look towards the introduction to the transformer model and the significance of attention is all you need model. Then we will talk about uh, a small activity that you'll have to do after this lecture, which is a case study analysis of transition from traditional AI to modern AI. So let us move forward. First, let us talk about exploration of early AI models that have been developed. So, what was perceptron theory? Let us start with there. What is perceptrons? So, the perceptron is a model of a biological neuron. It takes one or more inputs or stimuli and produces a binary output. The core components of a perceptron include first, input and weights. Each input is associated with a weight that determines its contribution to the perceptron's output. These weights are parameters that the perceptron adjusts during the learning process. Activation function. The weighted sum of the inputs is passed through the activation function, typically a step function. If the sum exceeds a certain threshold, the perceptron outputs 1, otherwise it outputs 0. Third, we have learning algorithm. The perceptron learns by adjusting its weights based on the error in its output compared to the desired output. Rosenblatt introduced the perceptron learning rule, a simple method for weight updates. Next, we have biological neuron versus artificial neural network. So, you can observe this image carefully. we have the neuron, as you can see, it has many input. It has dendrites, it has a nucleus, it has cell body, etc. But uh, on the other hand, the artificial neural network is actually just a mathematical model which accepts inputs through multiple layers of neurons. That is, we call the neurons. These balls that you are able to see here are called as neurons. So this is neuron number one, two, three, four, and they accept the feature set as inputs. Now these inputs are being passed and each input has a particular weight. Now these weights are represented by W1, W2, W3, W4. And these weights are being sent to the mathematical to do the weighted average in order to generate the output with the help of activation function. So this is just a background of what is artificial neural network. It is fine if you don't understand this in much detail, but you can always refer to this when you have a better understanding of the deep learning models. So let us move ahead. So let us talk about when should perceptrons be used. So perceptrons are the more are perceptrons are of the most complicated, uncomplicated varieties of machine learning algorithms designed to work on linearly separable datasets. Linear separability is a fundamental concept in machine learning and pattern recognition. It refers to the property of a dataset where two classes or categories of a data points can be separated by a straight line, that is, in two-dimensional space. A hyperplane in a higher dimensional space or a linear decision boundary in general. Linearly separable datasets are standard in simple problems where the classes can be distinctly separated. For example, a dataset of apples and oranges. Let us consider an example where we have a dataset that has images of or the data about apples and oranges. So when we plot these features like weight and color can often be separated using a single straight line. So let us talk about this example in a little detail. So, if you are able to observe the figure number A, let's say, let's say the red ones are the apples and blue ones are the oranges. So, when you are populating the data, you are able to understand that there is a single straight line that is able to pass between these two data points in order to classify them. But on the other hand, when you look at the B data set, you are clearly able to understand that there is no single line that you are able to draw in order to uh, uh, distinguish between them. So the data sets of these type of the type number A are called as linearly separable data sets. So linear separability is an essential concept because it influences the choice of algorithms and techniques for solving classification problems. When dealing with linearly separable data, simpler algorithms like logistic regression or linear support vector machines can often be used. For non-linearly separable data, more complex models like nonlinear SVMs and tree-based or deep learning models are necessary to capture the underlying patterns in the data. Understanding the linear separability of a dataset is a critical step in the feature engineering and model selection process while dealing with machine learning. So now we will talk about some basic components of perceptron. Uh, I'm sorry for the poor formatting, but please bear with me for that. Okay, so let us talk about some basic components of perceptron. So we have input nodes or input layer. This is the primary component of perceptron which accepts the initial data into the system for further processing. Each input node contains a real numerical value. Second, you have weight and bias. So weight parameter represents the strength of the connection between units. This is another most important parameter of a perceptron component. Weight is directly proportional to the strength of the associated input neuron in deciding the output. Further, bias can be considered as the line of intercept in a linear equation. Finally, you have the activation function. These are the final and important components that help to determine whether the neuron will fire or not. Activation function can be considered primarily as a step function. So there are some types of activation functions, just referring you for your reference. Also, I'll iterate this. If you're not able to understand this lecture a lot, it is fine. You can completely skip this lecture because this is a very detailed lecture, and it will, if you are able to understand even 10 to 20% of it, it will be very helpful for you when you are understanding how ChatGPT and other models work. So please bear with me for this lecture. Then we also looked into some types of activation functions that we have. So we have sine function, we have step function, we have sigmoid function, we do have actually a lot of other functions, but never mind. So these are some popular functions that we have, and this is again the same diagram that we saw on the previous slides. So next we will also discuss some type of perceptron models. So based on the layers, perceptron models are divided into two types. So there are single layer perceptron model and multi-layer perceptron model. So you can see the difference. There is this is only one layer, so we called it single layer. And then there are multiple layers. So here I have only shown two, but you can always have more than one layer. So these are called multi-layer perceptron models. So let us discuss the single layer perceptron model. So single layer perceptron models are one of the easiest artificial neural networks, that is ANN types. A single layered perceptron model consists of feed-forward network and also includes a threshold transfer function inside the model. The main objective of the single-layer perceptron model is to analyze the linearly separable objects with binary outcomes. In a single-layer perceptron model, its algorithms do not contain recorded data. So it begins with inconstantly allocated input for weight parameters. Further, it sums up all inputs or weights after adding all inputs. If the total sum of all inputs is more than a predetermined value, the model gets activated and shows the output value as +1. If the outcome is same as predetermined or threshold value, then the performance of this model is stated as satisfied and weight demand does not change. However, this model consists of a few discrepancies triggered when multiple weight inputs values are fed into the model. Hence, to find desired output and minimizing errors, some changes should be necessary to the weight outputs. So this is what is about single layer perceptron. A key highlight of single layer perceptron model is that it can easily recognize patterns which have linearly separable datasets. Next, we will talk about multi-layered perceptron model. Like a single layer perceptron model, a multi-layer perceptron model also has the same model structure but has a greater number of hidden layers. The multi, the multi, I'm sorry, the multi-layer perceptron model is also known as the backpropagation algorithm, which executes in two stages. First is the forward stage where activation function starts from the input layer in the forward stage and terminate on the output layer. Second, there is a backward stage. In the backward stage, weight and bias values are modified as per the model's requirement. In this stage, the error between actual output and demanded originated backward on the output layer and ended on the input layer. Hence, a multi-layered perceptron model has considered as multiple artificial neural networks having various layers in which activation functions does not remain linear, similar to a singular perceptron model. Instead of linear, activation function can be executed as sigmoid, tanh, relu, etc. for deployment. So these are just types of activation functions that we have. You will discuss more about this in the deep learning subject that you have in the upcoming semesters. A multi-layer perceptron model has greater processing power and can process linear and non-linear patterns. Further, it can also implement logic gates such as AND, OR, XOR, XOR, NOT, etc. in order to deal with the multi-layer complex datasets. Then we also have some advantages and disadvantages of multi-layer perceptron models. So a multi-layered perceptron model can be used to solve complex nonlinear problems. It works well with both small and large input data. It helps us to obtain quick predictions after the training. It helps to obtain the same accuracy ratio with large as well as small data. Next, we will look into some disadvantages of the perceptron model. In a multi-layer perceptron, computations are difficult and timing consuming. In multi-layer perceptron, it is difficult to predict how much that dependent variable affects each independent variable. The model functioning depends on the quality of the training. Next, we will look into some characteristics of perceptron. So the perceptron model has the following characteristics. Perceptron is a machine learning algorithm for supervised learning of binary classifiers. In perceptron, the weight coefficient is automatically learned. Initially, weights are multiplied with input features, and the decision is made whether the neuron is fired or not. The activation function applies a step rule to check whether the weight function is greater than 0. The linear decision boundary is drawn, enabling the distinction between the two linearly separable classes, +1 and -1. If the added sum of all input values is more than the threshold value, it must have an output signal. Otherwise, no output will be shown. Now, let us talk about some limitations of the perceptron model. A perceptron model has limitations as follows. The output of a perceptron can only be a binary number, that is 0 or 1, due to the hard limit transfer function. Perceptron can only be used to classify the linearly separable sets of input vectors. If input vectors are nonlinear, it is not easy to classify them properly. Next, let us talk about the future of perceptron. The future of the perceptron model is much bright and significant as it helps to interpret data by building intuitive patterns and applying them in the future. Machine learning is a rapidly growing technology of artificial intelligence that is continuously evolving and in the developing phase. Hence, the future of perceptron technology will continue to support and facilitate analytical behavior in machines that will, in turn, add to the efficiency of computers. The perceptron model is continuously becoming more advanced and working efficiently on complex problems with the help of artificial neurons. Next, we will look into the rise of deep learning, CNNs, RNNs, and the role of backpropagation. All right, so let us start with the rise of deep learning. Just give me a moment. Okay, so the rise of deep learning. The introduction. Let us go with the introduction first. So, deep learning, which is a subset of machine learning, has revolutionized the field of artificial intelligence or AI over the past decade by leveraging large data sets and powerful computational resources. Deep learning models have achieved unprecedented success in various tasks such as image and speech recognition, natural language processing, and autonomous systems. These technological advancements has opened new avenues for innovation and is shaping the future of many industries. This article delves into the historical context and breakthroughs and transformative applications that have marked the rise of deep learning. Next, let us have some historical context. First, let us know some early AI and machine learning. The concept of artificial intelligence dates back to the mid 20th century when pioneers like Alan Turing and John McCarthy laid the groundwork for the field. Early AI research focused on the symbolic reasoning and rule based systems, which, although promising, faced significant limitation in terms of scalability and adaptability. Machine learning, which involves the development of algorithms that enable computers to learn from data, emerged as a viable alternative. Early machine learning models such as decision trees, support vector machines, and logistic regression demonstrated potential but required manual feature extraction and were constrained by their inability to handle large scale data effectively. Next, we have the neural network renaissance. The concept of neural networks inspired by the human brain structure was introduced in the 1940s by Warren McClough and Walter Pitts. However, it wasn't until the 1980s that the neural networks gained popularity. Thanks to the development of the backpropagation algorithm by Geoffrey Hinton and David Rumelhart and Donald Williams, these algorithms allowed for the efficient training of multi-layer neural networks, paving the way for deeper models. Despite this progress, neural networks struggled to outperform traditional machine learning models due to limited computational power and small datasets. Let us look into some key breakthroughs in deep learning. First, the emergence of deep learning. The term deep learning refers to neural networks with multiple layers known as deep neural networks. The resurgence of interest in neural networks and the rise of deep learning can be attributed to three key factors: the availability of large datasets, advancements in computational power, and innovative algorithmic improvements. First, let us look at some data explosion. The proliferation of digital data driven by the internet, social media, and the digitization of various industries has provided deep learning models with vast amounts of training data needed to learn complex patterns. Datasets such as ImageNet, which contains millions of labeled images, played a crucial role in training deep learning networks. Computational advancements, the development of graphics processing units or GPUs and specialized hardware such as tensor processing units called as TPUs has significantly accelerated the training of deep neural networks. GPUs, with their parallel processing capabilities, enabled researchers to train deep learning models in a reasonable amount of time, making deep learning practical. Algorithmic innovations. Innovations such as a rectified linear unit or ReLU activation function, dropout regularization, and techniques like batch normalization have enhanced the training and generalization capabilities of deep neural networks. The development of architectures such as convolutional neural networks or CNNs and recurrent neural networks RNNs has further expanded the applicability of deep learning. 2. Landmark and achievements. Several landmark achievements have marked the rise of deep learning, demonstrating its superior performance over traditional methods and establishing it as a dominant force in AI. First, let us look at the ImageNet challenge in 2012. One of the most significant milestones in deep learning was the success of AlexNet, a deep convolutional neural network in the ImageNet Large-Scale Visual Recognition Challenge (ILSVRC) in 2012. AlexNet, developed by Alex Christgau, Ilya Sutskever, and Geoffrey Hinton, outperformed all previous methods by a significant margin, reducing the top 5 error rate from 26% to 15.3%. This breakthrough showcased the power of deep learning in image recognition and sparked a wave of research and development in the field. Next, DeepMind's AlphaGo in 2016. In 2016, Google DeepMind's AlphaGo defeated Lee Sedol, a world champion Go player, marking a historic moment in AI. AlphaGo combined deep learning with reinforcement learning and Monte Carlo tree search, demonstrating the potential of deep neural networks in mastering complex strategic games. This victory highlighted the ability of deep learning to tackle problems with vast state spaces and high dimensional inputs. Third, Transformer models in 2017. The introduction of the Transformer architecture by Vaswani et al. in 2017 revolutionized natural language processing or NLP. Unlike traditional RNNs, the transformer model utilizes self-attention mechanism, allowing it to capture long-range dependencies and parallelized training. Transformers became functional for subsequent models like BERT or bidirectional encoder representation from transformers and GPT generative pre-trained transformer, leading to state-of-the-art models such as ChatGPT. Next, we will look into some applications of deep learning. The versatility of deep learning has led to its adoption across numerous domains, transforming industries and enhancing everyday applications. Computer vision. So first application we will talk is computer vision. Deep learning has revolutionized computer vision, enabling machines to understand and interpret visual data. CNNs, with their ability to capture spatial hierarchies, have become the standard for image classification, object detection, and image segmentation. Applications include facial recognition, autonomous vehicles, medical image analysis, and more. Second, natural language processing. The impact of deep learning on NLP has been profound. Transformer-based models have set new benchmarks in tasks such as machine translation, sentiment analysis, text summarization, and question answering. These models have led to the development of virtual assistants like Apple's Siri, Amazon's Alexa, and Google's Assistant, enhancing human-computer interaction. Next, deep learning applications in healthcare. Deep learning is making significant strides in healthcare by enabling early disease detection, personalized treatment, and drug discovery. CNNs are deep generative models are used for diagnosing medical conditions from radiological images, predicting patient outcomes, and generating potential drug candidates. Next, autonomous systems such as auto driving vehicles. The rise of deep learning has propelled advancements in autonomous systems, including self-driving cars and drones. Deep reinforcement learning allows these systems to learn from interactions with their environment, improving their decision-making capabilities. Companies like Tesla, Waymo, and Uber are leveraging deep learning to develop autonomous vehicles that navigate complex urban environments. Next, we will see at future implications and challenges. The rapid advancement of deep learning presents exciting opportunities but also possesses significant challenges. Ethical considerations as deep learning systems became more integrated into society. Ethical concerns surrounding privacy, bias, and accountability arise, ensuring that deep learning models are fair, transparent, and do not perpetuate harmful biases is crucial for their responsible deployment. Interpretability and explainability. Deep learning models, often referred to as black boxes, lack interpretability, making it difficult to understand their decision-making processes. Research in Explainable AI or XAI aims to develop techniques that provide insights into how deep learning models make predictions, fostering trust and enabling their use in critical applications. Third, scalability and resource requirements. Training deep learning models requires substantial computational resources and energy, raising concerns about scalability and environmental impact. Developing more efficient architectures and training methods is essential to make deep learning sustainable and accessible in a broader range of applications. Next, we will look into the introduction of neural networks. Alright, so let us have some introduction to neural networks. So, neural networks are a subset of machine learning algorithms that are inspired by a structure and functioning of the human brain. They consist of layers of interconnected nodes or neurons which process data and learn to recognize patterns. Two widely used neural network architectures are convolutional neural networks and recurrent neural networks, each serving different types of data and applications. So let us first look into what are CNNs. CNNs or convolutional neural networks. So definition and purpose. Convolutional neural networks (CNNs) are specialized neural networks primarily used for processing grid-like data structures such as images. They are particularly effective for tasks involving visual data because they can automatically detect and learn spatial hierarchies of features, making them to go-to choice for image classification, object detection, and segmentation tasks. Next, let us have a look at some architecture of convolutional neural networks. So we have a convolutional layer, the core building block of CNNs. This layer applies a set of filters or kernels to the input image. These filters slide over the input data and compute the dot product, creating feature maps that capture different aspects of the input. For example, initial layers might capture edges and textures, while deeper layers capture more complex features like shapes and objects. Second, activation function. After the convolution operation, an activation function, typically ReLU, rectified linear unit, is applied to introduce nonlinearity. This helps the network to learn more complex patterns. Pooling layer. Pooling layers such as max pooling are used to reduce the spatial dimensions of the feature maps. This downsampling operation reduces the computational load and helps the network become variant to minor translations in the input image. Fourth, fully connected layer. In the final stages of a CNN, fully connected layers are used to classify the input into one of the desired output classes. This layer takes the flattened version of the pooled feature maps and makes predictions based on the learned features. Finally, we have an output layer. The final layer in a CNN typically uses a softmax activation function to output probabilities for different classes, assisting in classification tasks. Next, let us look at some applications of CNNs. So there are basic applications of CNNs are image classification, object detection, image segmentation, and face recognition. Next, let us have a look at recurrent neural networks or RNNs. Definition and purpose. Recurrent neural networks are designed to process sequential data by leveraging temporal information and maintaining memory of past inputs. They are particularly useful for tasks where context and order matter, such as language modeling, time series prediction, and speech recognition. Let us look at the architecture of recurrent neural networks. So, recurrent layer, the fundamental difference between RNNs and traditional feed-forward networks is the presence of loops. In RNNs, the output from previous time steps is fed back into the network along with the current inputs, allowing the network to maintain a memory of previous states. Second, there is a hidden state. RNNs have a hidden state that acts as memory which is updated at each time step. The hidden state is influenced by both the current input and the previous hidden state, enabling the network to learn dependencies over time. Activation function. RNNs typically use activation functions like tanh or ReLU to introduce nonlinearity. These functions help the network model complex temporal dependencies. Output layer. The output of an RNN can be a single value, many to one, a sequence, many to many, or can vary depending on the application. For example, in language translation, an RNN might output a sequence of translated words. So you can also see the diagram of recurrent neural networks. Next, there are some types of RNNs. So we have vanilla RNNs, we have LSTMs, and we also have GRUs. So vanilla RNNs, the basic form of RNN which can suffer from vanishing gradient problems over long sequences. Second, we have long short-term memory or LSTM, a type of RNN that addresses the vanishing gradient problem by using gates to control the flow of information, making it suitable for longer sequences. 3. Gated recurrent unit or GRU, a variant of LSTM with a simpler architecture and fewer parameters, making it faster to train while still handling long-term dependencies. So these are some diagrams that help you explain what is RNN, LSTM, and GRU. So you can just try to remember these words that I'm saying. You don't need to understand how they work, how they move forward. But in the coming deep learning series, you will able to understand everything of this in detail. But for now, just remember the words that I'm saying and uh, try looking around them around. Next, let us look at some applications of recurrent neural networks. So the first primary application is natural language processing. So tasks such as language translation, text generation, and sentiment analysis are done through natural language processing. Second, speech recognition. Speech recognition is converting spoken language into written text. Third, time series prediction, predicting future values based on past observation. Example, stock market or trends, etc. Next, let us look at the role of backpropagation in CNNs and RNNs. Definition of backpropagation. Backpropagation is a supervised learning algorithm used to train neural networks. It works by calculating the gradient of the loss function with respect to each weight in the network, enabling the network to learn by adjusting weights to minimize the loss. This gradient calculation is efficiently performed using the chain or a chain rule of calculus. This is how backpropagation works in a nutshell. You can also have a look at this diagram for better understanding. First, there is something called as forward pass. The input data is fed through the network to produce an output. In this phase, activations are calculated at each layer based on the current weights. Second, there is a loss calculation phase. The output is compared to the true label using a loss function. Example, mean squared error or cross entropy. So these are some examples of loss functions. You'll also be discussing them in the deep learning lecture. The difference between the predicted output and the true output is quantified as the loss. Backward pass, the loss is propagated backward through the network. Starting from the output layer, the algorithm computes the gradient of the loss with respect to each weight using a chain rule. This involves calculating the derivative of the loss function concerning the weights and activations at each layer. Fourth, the weight update. Once the gradients are computed, the weights are updated using an optimization algorithm. Example, stochastic gradient descent or ADAM. The weights are adjusted in the opposite direction of the gradient to minimize the loss. Now let us have a detailed look of backpropagation in CNN and backpropagation in RNN. In CNNs, backpropagation is applied to both the fully connected layers and the convolutional layers. The gradients of the filters in convolutional layers are computed by convolving the gradient of the loss with the input data. This enables CNNs to learn which features, example edges, textures, objects, are important for a given task. Backpropagation in RNNs. For RNNs, backpropagation is extended over time, known as backpropagation through time (BPTT). Since RNNs deal with sequential data, the error is propagated back through each time step, and gradients are calculated for each parameter at each time step. However, RNNs can suffer from the vanishing gradient problem, making it challenging to learn long-term dependencies. LSTM and GRU architectures help mitigate this issue by using gating mechanisms. Next, finally, we will look at the transformers. So transformers is one of the most important concept that is being used in the AI and machine learning world. So when you look at transformers, it is all about generative AI. So generative AI, the core or heart of generative AI is the transformer model, which is working. So transformer model was actually proposed in a research paper in 2017 called as Attention is All You Need. So the Attention is All You Need is the go-to paper which has revolutionized the generative AI or kick-started the generative AI field of artificial intelligence. So let us have a brief look at generative AI. Transformers, the backbone of modern NLP. Introduction to Transformers. Transformers are a type of deep learning model introduced in the paper Attention is All You Need by Vaswani et al. In 2017. They have revolutionized natural language processing and are the foundational architecture behind the state of the art models like BERT, GPT-3 or ChatGPT, and T5. Unlike previous models like RNNs and LSTMs, which process data sequentially, transformers handle data in parallel, making them significantly faster and more efficient, especially for large datasets. The architecture of transformers. So the transformer model consists of an encoder and a decoder. Both components use stacks of identical layers, typically 6 to 12, depending on the implementation. Each layer in the encoder and decoder is made up of two sublayers. One is multi-head self-attention mechanism and second is feed-forward neural network. The multi-head self-attention mechanism. This is the core innovation of the transformer. It allows the model to focus on different parts of input sequence simultaneously, effectively learning contextual relationships between words regardless of their position in the sequence. The feed-forward neural networks, following the attention mechanism, each layer has a position-wise fully connected feed-forward network that further uh, processes the information extracted by the attention sublayer. Each layer in both the encoder and decoder also includes residual connections around each sublayer, followed by layer normalization to stabilize the accelerate training. So you can quickly have a look at the transformer diagram. You can see the encoders and the decoder. So the encoder block consists of a multi-head self-attention block with a feed-forward network, and then it has similar encoders. So there are typically 6 to 12 encoders in each transformer block, and then there is a decoder which accepts the output from the encoder and creates the original uh, output. Next, let's have a look at the most important mechanism called as the attention mechanism. This was proposed in the paper called Attention is All You Need. So, attention mechanism, the heart of transformers. The phrase attention is all you need encapsulates the primary innovation of the transformer model. The attention mechanism allows the model to selectively focus on specific parts of the input sequence while processing. This is crucial for understanding context and relevance, especially in language tasks. Self-attention in a self-attention. In a sentence, each word might relate to the other word. Self-attention allows each word in a sentence to pay attention to every other word, weighing the importance of each word's contribution to the sentence representation. It computes a score for each word pair and uses these scores to weigh the word's contribution to the output. Multi-head attention. Instead of a single attention score, multi-head attention uses multiple sets of attention scores, each capturing different types of relationships and patterns. This mechanism provides the model with multiple perspective on the input sequence, enhancing its ability to capture more nuanced relationships. So let us have a simplified explanation of whatever I said related to the attention mechanism. Input representation. Each word is represented as a vector. The input sentence is transformed into these vectors using an embedding layer. So there is something called as query, key, and value. For each word, the model generates three vectors: query, key, and value. The query vector represents that what the current word is looking for. The key represents what the other word offer, and the value is the actual information of the word. Score calculation. The model calculates the score using the dot product of the query and key vectors, indicating how much focus should be given to the respective words. Weighting and output. The scores are normalized using a softmax function to generate weights. These weights are then used to create a weighted sum of the value sectors. resulting in a new representation of the word that captures the context of the entire sentence. Let us look at some benefits of benefits of transformers and the attention mechanism. First, we have parallel processing. Transformers can process words in a sequence simultaneously, unlike RNNs and LSTMs that process sequentially. This reduces training time and makes it feasible to train on large datasets. Long distance dependencies. Attention allows the model to focus on relevant parts of a sentence, regardless of the distance between words. This is particularly useful for understanding context and relationships in complex sentences. Scalability. Transformers transformers scale efficiently with the size of the data and model. As more data and computational power are available, transformers can continue to improve performance. Flexibility. The same transformer architecture can be used for a wide range of tasks, including text generation, translation, and summarization, by modifying the input and output formats. Next, let us have a look at some applications of transformers. Transformers have found widespread use in various NLP applications. First is language translation. By capturing contextual meaning, transformers excel in translating text from one language to another, capturing nuances and context more effectively than previous models. Text generation. Models like GPT-3 can generate coherent and contextually relevant text, enabling applications like chatbots, content creation, and interactive storytelling. 3. Sentiment analysis and classification. Transformers can analyze the sentiment of a text, classify it into categories, and understand the underlying tone and intent. Question answering, and information retrieval. Transformers can understand and answer questions based on provided context as seen in models like BERT. Finally, we will have a case study for you to understand more about the generative AI and attention mechanism. Transition from a case study analysis. The case study is about transition from traditional AI to modern generative AI. All right. Transition from traditional AI to modern generative AI. Artificial intelligence (AI) has undergone significant transformation over the years, moving from traditional AI, characterized by rule-based systems and machine learning models, to modern generative AI or Gen AI technologies. This case study explored this transition, focusing on how companies and industries have adapted to the shift, the challenges faced, and the benefits reaped from leveraging GenAI. Let us look at some foundations and limitations of traditional AI. Rule-based systems. Early AI systems relied heavily on predefined rules and logic, where human experts encoded knowledge into the system. These systems worked well for structured problems, but struggled with more complex, unstructured tasks. Second, machine learning. Traditional AI began incorporating machine learning, allowing systems to learn from data rather than relying solely on human defined rules. Techniques like decision trees, support vector machines, and early neural networks enabled AI to handle more complex tasks. Third, supervised learning. Most traditional AI systems relied on supervised learning, requiring large labeled data sets. The AI learned by example, making predictions or classifications based on historical data. Next, let us have a look at some limitations. Limitations: data dependency. Traditional AI systems required massive amounts of labeled data to train effectively, limiting their application where labeled data was scarce or expensive to acquire. Scalability. Scaling traditional AI systems to handle diverse real world scenarios often required significant engineering effort and expertise. Lack of creativity. Traditional AI was often confined to the boundaries of the training data, lacking the ability, excuse me, lack of creativity. Traditional AI was often confined to the boundaries of the training data, lacking the ability to generate novel content or insights beyond what had seen. So here's a small diagram that represents limitations of generative AI. First, it is limited by training data, struggling with true creativity, lacking nuanced understanding, difficulty with adaptability, and data privacy and security. Next, we'll look into the rise of generative AI. Generative AI represents a significant evolution in AI capabilities, characterized by its ability to create new, original content. Technologies like generative adversarial neural networks or GANs, variational autoencoders, VAEs, and large language models (LLMs) like GPT-3 and GPT-4 have pushed the boundaries of what AI can achieve. Key features of generative AI. So first key feature is content generation. Unlike traditional AI, Gen AI can generate new content, whether it be text, images, music, or even videos. The ability opens up possibilities for creative applications. Second, unsupervised and self-supervised learning. Gen AI models can learn from vast amounts of unlabeled data, making them less dependent on labeled datasets and capable of uncovering hidden patterns in data. Third, contextual understanding. Modern AI or Gen AI models have shown remarkable ability to understand and generate human-like uh, human-like uh, context and engage in meaningful conversations. Next, we will have a look at transition from traditional AI to Gen AI, a small case study. So, this is a case study of OpenAI's transition to generative AI. Background: OpenAI, an AI research and development company, initially focused on traditional AI methods. However, the limitations of traditional AI pushed OpenAI to explore generative models, leading to the development of breakthroughs models like GPT-2 and GPT-3. The phase of transition. First, exploration and research. OpenAI invested heavily in researching generative models, exploring different architectures, and experimenting with unsupervised learning techniques. The goal was to create models that could not only predict outcomes but also generate content. Building large scale models. The transition required the development of large scale models trained on massive datasets. OpenAI used transformer architecture, which allowed the model to process and generate human-like text. The scaling of model parameters was crucial to improve the quality and contextual understanding of the generated content. Computational infrastructure. Moving to GenAI required a significant investment in the computational resources. Training models like GPT-3 involved using state-of-the-art GPUs and distributed computing. This phase highlighted the importance of the infrastructure in the transition to modern AI. Finally, we have fine-tuning and deployment. Once the base model, Once the base models were trained, they were fine-tuned for specific applications. OpenAI introduced a reinforcement learning framework with human feedback (RLHF) to refine model outputs based on on user interaction. This step was critical in aligning the model's behavior with human values and expectations. Next, challenges faced. The first challenge is ethical considerations. With the power to generate realistic content, concerns around misinformation, deepfakes, and misuse of technologies arose. OpenAI had to implement ethical guidelines, usage policies, and guardrails to prevent misuse. Computational costs. Training large generative models is resource intensive, requiring significant financial investment. OpenAI had to manage the trade off between model performance and computational efficiency. Third, model bias. GenAI models can inadvertently learn and propagate biases present in the training data. Addressing bias and ensuring fairness in model outputs become a critical challenge. Fourth, data privacy. The use of massive datasets for training raised concerns about data privacy and the possibility of models inadvertently memorizing sensitivity. Next, outcomes and impact. First is new product offerings. The development of GPT-3 enabled the creation of new products and services, such as OpenAI's API, which business could integrate into their applications to provide advanced conversational AI capabilities. Advancement in research. The transition to GenAI positioned OpenAI as a leader in AI research, pushing the boundaries of what was possible and influencing the broader AI research community. Wider adoption. The success of GenAI models led to their adoption across various industries, including healthcare for diagnostic and patient interaction, education, personalized learning and tutoring, and entertainment content creation. Increased revenue streams. Offering access to powerful generative models opened up new revenue streams for OpenAI through licensing partnerships and API usage fees. Applications in other industries. First is healthcare. GenAI models are used to generate synthetic medical data, assist in diagnosis, and provide personalized patient care through intelligent virtual assistants. Second, finance. Financial institutions leverage GenAI to generate market insights, simulate economic scenarios, and create personalized financial advice for clients. Media and entertainment. Gen AI is used to create music, write scripts, generate graphics, and even develop virtual characters, revolutionizing content creation, marketing, and advertising. Companies use Gen AI to create personalized advertisements, generate marketing copy, and analyze customer sentiment, improving engagement and customer experience. Finally, let us have a conclusion. The transition from traditional AI to generative AI marks a paradigm shift in how AI technologies are developed and deployed. Generative AI's ability to create, understand, and engage has opened new frontiers in creativity, efficiency, and problem solving. Organizations making this transition need to consider not only the technical challenges but also the ethical and societal implications. As Gen AI continues to evolve, its integration into various sectors will likely become more seamless, bringing profound challenges to industries worldwide. So, this is what we discussed in a nutshell in today's lecture. We discussed about attention mechanism, we discussed about transformers, we also discussed about how traditional AI and generative AI or attention is all you need paper connected. Now we will look into some popular AI tools in the further lectures to discuss more in the Gen AI field. Thank you so much for being with me.